Alright, let's get started. Last lecture we got into our first major topic of analytical chemistry. That would be acids and bases. Most of this should feel like a review even if you don't clearly remember it, and most of it we will relearn by actually using in problems, which we're going to start getting into today. But briefly, we went over the definition of an acid and a base that we will be using in this class. Acids are proton donors and bases are proton acceptors. And we can see those definitions in action in this sample acid-base reaction here, where we have the classic weak base ammonia reacting with water. And water can function as an acid or a base, it depends on what it's paired up with. In this case, it's with a base, so it will behave like an acid. So we see what happens is the NH3, like a base, takes a proton from the water, forming NH4+. In the meantime, water clearly gave away its proton, like an acid, leaving behind hydroxide. Now, we call these products the conjugate acid-base pair, and that's because an equilibrium is reached. And when we think about the reverse reaction that occurs, each of these behaves like an acid and a base. And we can see NH4+ behaves like an acid. It gives away its proton to form NH3. OH- takes that proton to form H2O. In other words, OH- is acting like a base. So we call this the conjugate acid and this the conjugate base. Another concept we got into was the idea of acidity and basicity. And we started by first defining this equilibrium constant called Kw, the water dissociation constant. And this relates to the equilibrium between protons and hydroxide ions in water. And that Kw is 1.0 times 10 to the minus 14, provided we're at 25 degrees Celsius, which we will always be in this class unless otherwise specified. And what's very important, as we'll see later today, is that this Kw always applies if the solution is aqueous. In other words, even if your aqueous solution has more protons than hydroxide ions, these two concentrations better still multiply out to 1.0 times 10 to the minus 14 if this is taking place in water. If we do have more protons than hydroxides, our solution is acidic and the pH will be less than 7. The final concept that we reviewed was the pH, which is just the negative log of the proton concentration. We learned that only numbers to the right of the decimal point are significant after you do a log. We also learned how to go backwards from a pH value to the proton concentration. And pH values will be a major topic in today's lecture. So let's get started. So often when I hear the word acid, I think of Batman. And that's because there's this famous story about how his arch nemesis, the Joker, became a clown in the first place. He fell into a vat of acid, and yeah, that somehow turned him into a clown, because comics. Believe it or not, this is going to show up on exam 1. Although you don't need to be familiar with Batman or comics or anything like that. We're going to talk about the acid part of the story. So let's recap the definitions of strong and weak acids and bases. Strong acids and bases ionize, in other words, they react 100% in solution. The reaction essentially goes to completion. On the other hand, weak acids and bases only partially ionize. Their reactions reach equilibrium. A weak acid only dissociates so much into protons and a remaining anion before these two start to react together and reform HA, our weak acid, and an equilibrium is reached. And because there's an equilibrium, there must be a K value. And we give the special subscript A to denote that this equilibrium is an acid dissociation equilibrium. And this Ka expression will always look like this because all acid reactions in water do the same thing, no matter how complicated the acid is. Split into a proton and leave behind some anion, and those will always be your products, and the weak acid will always be your reactant. Weak bases are very similar, except the base will react with water, take a proton away, forming BH+, and leave behind hydroxide, and there's a Kb expression for this equilibrium, and it looks very similar to what we saw over here. Now, one possible point of confusion to clarify is that our base reaction has the water clearly written in it, whereas the acid reaction doesn't show water. And this is something that I brought up in the last lecture. We always need to recognize that there is no such thing as a proton swimming by itself in aqueous solution. That proton always finds a water and in fact forms hydronium ion. H plus is just a shorthand, but what's really happening is HA does in fact react with water to form H3O plus and the resulting anion. In the case of the weak base, we have to write the water. We can't do a shorthand because if we ignored this and just wrote B, well, how do you explain how this happens? So from there, let's talk about how the size of K correlates to acid or base strength. The larger the K value, the stronger the acid or base. And we can see that in the math, right? If this value here is larger, it would imply that the ratio of H plus produced versus HA remaining must be increasing for this value to get bigger. In other words, more of our acid is dissociating to produce protons, and that would imply you have a stronger acid. A similar argument can be made for Kb. A larger K value here would imply a higher hydroxide concentration produced from the reaction of base. And so to summarize this slide, let's just write the note higher Ka/B, higher Ka/B means we have a stronger acid/base. Stronger acid/base. And then we'll make another note for strong acids and bases. For strong acids and bases, the Ka or B values are greater than 100, if not a million. In other words, those K values are so large that there's effectively nothing but product and very little reactant left, which is why we say effectively strong acids and bases react all the way to completion. Next, I want to discuss how the Ka and Kb of a conjugate acid and base pair relate to their relative strengths. So let's call this section Ka, Kb, and strength. And while we cover this, we're going to learn something that probably flies in the face of something that you once learned. And also we'll understand why a very important relationship that you would have been taught in Gen Chem exists in the first place. So let's start by writing a generic acid equilibrium with water. Acid equilibrium with water. And if we're talking about equilibrium, we're implying that we're talking about a weak acid, HA. And I'm going to be super specific and accurate and write that it's really reacting with water. I'm not going to use the shorthand. So H2O, and I'll write liquid to specify that this is the very concentrated liquid that everything else is dissolved in. But I'm not going to bother writing aqueous. Much like what we've seen in the past, when no phase is specified, aqueous is implied. This achieves an equilibrium with H3O plus and the remaining anion, A minus, which will be the conjugate base of that acid. If this weak acid was acetic acid, which is a very classic weak acid, the Ka value that we would find is 1.8 times 10 to the minus 5. Now notice that that K value is well below 100, so this is definitely a weak acid based on the standard we wrote in the last slide. So ask yourself, based on your memory of Gen Chem, is this acid's conjugate base weak or strong? Let's find out. So the conjugate base reaction in water will look like this. Conjugate base equilibrium with H2O. Well, that A minus, that conjugate base, can also react with water once it's formed and act like a base. It will take a proton from the water, reforming HA and leaving behind hydroxide, which is what we would expect the base to ultimately produce. and its Kb value is currently a question mark. We'll solve for that momentarily, but first let's figure out how we could solve for that based on a very important relationship that you should remember from Gen Chem, but you might never have known why this relationship works. And it relates to the manipulating equilibrium constants concept that we learned about in Lecture 3. Let's recall what happens if we were to add two equilibria together. Well, we would treat it like an algebra problem, and we can see that we have certain species that appear on both sides of these two reactions, and we can cancel them out. When I do that, I'm left with 1 plus 2 waters, so H2O plus H2O. Again, we'll keep specifying that these are liquids, are in equilibrium with H3O plus and hydroxide ions. And that equilibrium is something we've seen before, right? That's the autoionization or protolysis equilibrium for water. And we know that that equilibrium has a very specific K value, Kw. But we also know that that Kw must be equal to the K values of the two reactions that we're adding together, because we learned that during the manipulating equilibria section. That's why I said that that concept would be important for acids and bases. The second reason we would learn these concepts is because they'll be important for understanding acid and base equilibria later, so I'll bring it back then. And so two important ideas to take note of. This equilibrium is always present in aqueous solutions, and we wrote a note like that when we first learned about Kw in the previous lecture, but this is why that note was written, that no matter what acids and bases we have, we will always have this equilibrium happening in the background. So regardless of the H3O plus produced by an acid or the hydroxide produced by a conjugate base, at the end of the day, the H3O plus and hydroxide will find concentrations that multiply to Kw because this equilibrium is always present in the background. The other idea to take note of is that this relationship will always exist for conjugate acid-base pairs. And you should recognize that formula from Gen Chem, but this is the logic of why it works. And so if I wanted to solve for the Kb of this acid's conjugate base, I would just take the Kw, 1.0 times 10 to the minus 14, divide it by the Ka, which we see above, 1.8 times 10 to the minus 5, and solve. And we get 5.6 times 10 to the minus 10. That is the Kb for this base. So is that a weak or strong base? And how does that compare to what you thought the conjugate base's strength would be?
Some of you may have thought that the conjugate base of a weak acid like acetic acid would be a strong base. And that's because at some point you probably heard the phrase, strong acid is conjugate to a weak base, and vice versa. If that's the case, you need to delete that phrase from your mind and replace it with a subtly different phrase. A stronger acid is conjugate to a weaker base, but they might both still be overall weak. Really think on that, meditate on it for 15 seconds. And now let's get into what I mean by that.
So to rationalize how this all works, we have to acknowledge that there are really three different classes of acid strength. So let's write that. 3 strengths. There's strong, which we know the definition of, 100%, that hasn't changed. There's weak. And then there's the third class that you haven't really heard of probably, and that's the ineffectively weak. So weak that basically no reaction even occurs, 0%. And a strong acid is conjugate to that ineffectively weak base. Not a weak base, an ineffectively weak base. Strong acid conjugate to ineffectively, let's underline that, ineffectively weak base, and vice versa. For example, if we use the classic strong acid HCl, and we didn't use shorthand, we wrote HCl reacting with water, we know it will 100% react to produce H3O plus and leave behind Cl minus, which in theory is the conjugate base. And so if we were to look at what Cl minus's reaction with water would be, we would get the following. Cl minus would react with water, and if Cl minus is a base, then in principle it should take a proton, reforming HCl and leaving behind hydroxide. What's the matter with what I just said? Pause the video and think about that for a moment. The problem is that I just said that this reaction forms something that doesn't actually form in water. It breaks apart. If HCl 100% breaks apart, then that means it can 0% come back together, which is what this reaction is implying would happen. So this makes total logical sense. A strong acid's conjugate base can't effectively react in water because it would just reform a product that is meant to split apart 100%. And so this reaction does not occur. Too weak for reaction to occur. As for weak acids, well, they're conjugate to weak bases. Weak acids are conjugate to weak bases. We'll abbreviate conjugate. Weak acids are conjugate to weak bases. But a less weak acid means a more weak conjugate base, and vice versa. But a less weak acid, let's put less weak in quotes, a less weak acid is conjugate to a more weak base, and vice versa. So let's end the video by seeing that last statement in action. So here's acetic acid, which we mentioned earlier. Weak acid, Ka 1.8 times 10 to the minus 5. We already solved for its conjugate base, acetate ions, Kb value, which is 5.6 times 10 to the minus 10. Both clearly less than 100, both weak. And we would say that this base here is a weaker base than that is an acid, because that's a smaller K value than over here. Now let's look at formic acid. HCO2H, Ka is 1.8 times 10 to the minus 4. Still a weak acid, but not as weak as acetic acid. It is a larger Ka value. Well, if we were to solve for its conjugate bases Kb, we would get 5.6 times 10 to the minus 11. So this is an even weaker base than acetic acid's conjugate base. If we did another example, HC3O3H3, our Ka is even larger than formic acid's, and the corresponding conjugate base has an even lower Kb than formic acid's conjugate, formate ion base. And so this is what I mean. As a weak acid's Ka goes up, or its strength goes up, its conjugate weak base's Kb, or strength, goes down. And so we do have this inverse relationship. But let's be clear. Everything on the board right now is considered weak. Their Ks are well below 100. To give some contrast, HCl has a K value that's over 1 million. And if we were to solve for Cl minus's Kb, it's times 10 to the minus 21. It's so tiny, it's pathetic. It doesn't really do anything. And we call that an ineffective base. So here we see strong is conjugate to ineffective, but weaks are conjugate to weaks. It's just that a less weak acid has a more weak conjugate base. And so to summarize some important relationships, I tell you what that song's title has to do with acid, but that would be inappropriate. Instead, I'll just point out these relationships here. We've just spent some time on the top half discussing how Kw relates to both proton and hydroxide concentration, and now to the Ka and Kb of a conjugate acid-base pair. If you do some log trickery, you can come up with those p-value relationships that you see below, but the one that's really important is that pH plus pOH equals 14, which we'll just learn later when we see it in action.
All your base are belong to us.
And I'm not even going to attempt to explain what all your base are belong to us means. But if you're curious about how stupid things were when I was in college, look it up. Anyways, here's a clicker, and here's another one. We'll do them in Zoom.